Good morning, everyone, and welcome to the next installment of the Specialist Maths Student Revision Tutorials presented by Texas Instruments Australia. My name is Stephen Crouch. I'm a teacher at Frankston High School. Let's get started. Today we're doing Vectors Part 2. This is a continuation from the previous Vectors Part 1, which I presented as well. In today's session, we'll be doing a couple of things. First of all, we're going to be looking at scalar and vector resolutes. So we'll review those concepts as well as go through a couple of questions. Next, we're going to look at linear dependence and independence, including a few examples to show you how to use the CAS effectively in that concept. And finally, we're going to look at vector proofs and how we can use the dynamic geometry facility in our handhelds or computer software to be able to verify certain concepts that we get with vector proofs. And finally, the main thing really is we can look at strategies on how we can use our handhelds to solve exam-style questions. Okay, so let's get started. So here we go. Here's a summary of what we're going to go through today. Okay, so first of all, let's start with scalar resolutes. So you might know this already very well. The scalar resolute of a vector in the direction of another is simply the dot product of the first vector with the unit vector of the second. There's two alternative formulas for it. You can use either one of those. Computationally, in terms of by hand methods, I reckon the first one's easier to use, where you dot product the two vectors and divide by the magnitude of the second. If you're using the CAS, it's a lot easier to just use v dot w hat. Just as a quick reminder and recap from Vectors Part 1, the magnitude of a vector is found using the norm command, which was in menu 771. And to get the unit vector of any given vector, you simply use the unit v command, which is menu 7c1. Okay, so what I'd like to start off with is to look at what the definition of a scalar resolute is from a visual perspective. So I've got two vectors here. I've got vector A and vector B. As you can see, I can drag vector A around, and I can also drag vector B around. Just for this moment, I'm going to keep vector B horizontal with respect to my screen over there. However, I can also move B around as well. But to keep things simple, I'll keep vector B down the bottom there. So the scalar resolute, the easiest way, I reckon, to visualize what's going on is via a light. So just imagine there's a light that's above vector A over there, and vector B is along the ground. The easiest way to describe the scalar resolute is to take vector A and imagine that it's an object such as a pole or a rod or a broom or a ladder or anything like that that's hanging on the side like that. And this light is shining perfectly vertically, so there's no spread really like that. It's shining vertically, but also it's shining vertically in such a way that its range is the horizontal part of vector A. What you might notice is I've got this gray shadow at the bottom of here, and as I move vector A around, look at the length of the shadow here. So I've got the length of the shadow in whatever units we're looking at, and as I increase the length of A as well as decrease the angle, I've got the shadow increasing as well. So as you can see, if I make A completely vertical, that shadow basically disappears because there's no pole or lamp or anything there to sort of shine rays of light on it. So that is probably one of the easiest ways to describe and also understand what the scalar resolute is. It can be thought of as the length of the shadow that's projected by a light shining on vector A vertically. Okay, so moving on to an example. Let's find the scalar resolute of vector v, which is 3i minus 2j plus 5k, in the direction of another vector, w, which is 2i minus j plus 2k. So I'm going to define the vector as I did before, which is control and the template button to get the assign to command. So v is assigned to the vector. So you use vectors to define a vector. It's control and open bracket. So I'm going to put the components separated by commas. So 3, comma, -2, comma, 5. So that's vector v. Let's do the same for w. W control template, control open bracket, and I've got 2, comma, -1, comma 2. There we are. So you've got V and W. So the formula that's best for CAS is the dot product of V and the unit vector of W. So to get the dot product, I'm going to press menu 7C3. Menu 7C3 gives us a dot product. We're going to use var to get to V, comma, and I want the unit vector of W. So unit vector of W is menu 7C1. So menu 7C1 gives us unit V, and I go to var, and again, I've got W, it's enter, and there we go, we've got 6. So if you drew vector V and vector W, the effective length of the shadow that vector V would project in the direction of W would be 6 units long. So that's using the scalar resolute formula. Let's now move to an exam question where we get to explore the scalar resolute in a slightly higher level. Okay, so we've got a triangle that has vertices at the origins. We've got a 3D Cartesian axis here. Vertices at the origin, at the point A, 5, -3, -2, and the point B, 1, -2, -2. So our job, first of all, is to find the scalar resolute of OA in the direction of OB, and use this, hence, to find the height of the triangle OAB. Okay, so this is quite an advanced question, and in order to really get full use out of this, we need to look at a diagram. So I've created a diagram over here, which shows us the vectors OA and OB. Not only that, if you might notice this orange dashed line over there, that right there is basically the side length AB. Now I've tried to get the angle in such a way, the viewpoint rather, in such a way that you can see the triangle as best as possible. So this is a three-dimensional axis here. You've got X, Y pointing left, and Z basically pointing out of the page. Okay, so first of all, I'm going to show you what the scalar resolute is. So if you take the scalar resolute of OA in the direction of OB, I will do the calculation in a minute. If you take the scalar resolute, what you get is this magenta vector. This magenta vector is really starting at the origin. So what you can see is if I place a light around here, around where my mouse is pointing at the moment, and you shine it, the shadow actually extends past the vector OB. So this is one of those things about scalar resolutes, or even vector resolutes for that matter, is the resolute does not necessarily have to be shorter or of a smaller length than the vector you're projecting onto. It can be longer, as you can see over here. So this magenta vector starts at O and ends up at this point over here. So if you want the height of the vector, it's this green line over here. So the angle between the green line and this magenta line is a right angle, and that is the triangle over here. So the triangle is comprised of the blue side, the red side, and the orange side. And to get the height of it, the green dotted line basically will, the length of that will be the height of the triangle. Okay, so let's think about what we might do as a calculation. So when you do find the scalar resolute, it will be the length from O to this pink, to the magenta head over there. And if you want the height of the triangle, which is the green dotted line over there, we can use Pythagoras for that. So you just need to find the length of vector OA, and then use Pythagoras basically in reverse with the length of the scalar resolute, and that will get us the height over there. Okay, so let's now perform the calculations required. So let's go and define a couple of all these vectors over here. So I'll first define OA. So OA is defined as vector 5, -3, -2. So even though I've got coordinates over here, it helps that we're starting all our vectors at the origin, which means our position vectors are simply the coordinates themselves. The components of the vectors are the coordinates themselves. Okay, so now let's do OB, do the same thing as well. So OB is defined as 1, -2, -2. Okay, so let's now find the scalar resolute of OA in the direction of OB. So menu 7C3 will give us dot product, and I want OA, I'll just type that one out, comma, we want the unit vector of OB. So menu 7C1 unit vector of OB. There we go. So that is 5. So 5 is the length of the shadow. It's basically from O all the way up this magenta vector that has a length or a magnitude of 5. So to use Pythagoras, I will need the length of OA. To get the length of OA, I will need the norm command. So norm command is menu 771. So the norm, I want to find the norm of OA. It's square root 38. Okay, so what that means is this blue vector here has a length of root 38. The magenta vector has a length of 5. So I'm going to use Pythagoras to do that. So using some basic Pythagoras, the length or the height of OAB will be the square root. So square root of OA squared minus the scalar resolute squared. Enter, and we get root 13. So to answer the question, the scalar resolute of OA in the direction of OB, that was 5, and hence the height of triangle OAB is square root 13. I'll just quickly show the diagram again so you can see what we found, that this green dotted line has a length of root 13. Okay, so moving on now to vector resolutes. So again, just like scalar resolutes, vector resolutes have two different forms of here. In terms of a by-hand approach, I reckon v dot w over magnitude w squared multiplied by w is probably easier to do by hand. And if you're using the CAS, you can use v dot w hat all multiplied by w hat. So the big difference really between a scalar and vector resolute is that a scalar, as the name implies, is a scalar. It has no direction. It only has a magnitude. Whereas a vector resolute is in fact a vector itself. So in terms of the previous example over here, this magenta vector starting at O and ending at this point over here is a vector, and that would be the vector resolute of OA in the direction of OB, whereas the length of that vector is the scalar resolute, which is why I made a note over here that the length of the vector resolute is equal to the scalar resolute. So the other vector resolute we do is the one that's perpendicular to the vector W, and that's simply defined by V minus the vector resolute in the parallel direction. So again, just as I did with scalar resolute, I'm going to use a diagram to show what's going on. So again, I've got the exact same diagram. I've got vector A and vector B. So I'm going to turn the light on again. So we've got this light. And again, what you see, the difference here between this diagram and the scalar resolute diagram is that the shadow now is in fact a vector. So if you recall back in the scalar resolute diagram I just had a line segment over here. Now I have a vector. So the easiest way to describe the vector resolute parallel to another vector is simply the vector that describes the shadow emanating from the base of A and then along the direction of B. But with vector resolutes, we also have a second vector, which is the one that's perpendicular. So again, if I can grab A, and you can see what's happening. So as I grab vector A and move it around, I've got a component that's parallel to vector B, and I've got a component that's perpendicular to vector B. What I will like to mention as a very important point is that the two resolutes that we find, so one is the gray vector, which is the resolute parallel to vector B, and the orange vector, which is the vector resolute perpendicular to vector B, those two vectors add up together to create vector A, and also they're perpendicular to each other. So those properties are very important, and you will see that soon in a couple of questions' time. Okay, so moving on to a question where we just get to use the vector resolute formulas. So again, I've got vector V and vector W, and our job is to express the vector V as a sum of two resolutes, one which is parallel to W and the other which is perpendicular to it. So I will make a note that it is not sufficient to just find the resolutes. You need to then express the answer as a sum of these two resolutes. Okay, so let's get started just by defining these vectors. So V is defined as, let's type in the vector, 3, -4, 1. And W, same deal, define as vector 1, -2, 3. There we go. So let's now find the vector resolute of V parallel to W. So what I can do is I can use the formula for it, and which is the dot product. So menu 7C3 dot product of V, comma, and then menu 7C1, which is the dot product of V and the unit vector of W. And then I need to multiply that by the unit vector of W. So again, menu 7C1, unit vector W. There we go. So this vector here, 15 on 14i minus 15 on 7j plus 45 on 14k, is the vector resolute of V in the direction of W. Okay, so what you could possibly do as well to save yourself a bit of time, you can define the unit vector of V, or unit vector of W, sorry, I should say, as something like W hat. But I'll leave this at the moment. And I want to find the perpendicular resolute. So the perpendicular resolute, according to the formula, is V minus the previous result of here. So I just pressed up, enter, enter again. There we go. So I've now got the two vectors. I've got this is the vector resolute of V parallel to W, and this is the vector resolute of V perpendicular to W. Now, I could add them on the calculator, but of course, when I ask the calculator to add it, it will simply give me back V. So let's test out that theory. I'm going to press up a couple of times. There we go. That's the parallel resolute plus the perpendicular resolute. And when I hit enter, I should get V back again. No, not getting V. What's going on? Have I done it properly? Unit vector of W. 1, 2, 3, 3. Sorry, I just realized I probably should define V again. I stopped with the definition. There you go. Sometimes these things happen. So 3, neg 4, 1. Let's quickly fix that. Sorry about that error, everyone. So control there. W is defined as vector 1, neg 2, 3. Okay, should double check my typing as I go along. Okay, so again, let's just quickly get through the dot product. So dot product of V and the unit vector of W multiplied by the unit vector of W. Okay, so that is my vector resolute of V in the direction of W. And what you might notice is it's exactly equal to W, which is telling me that the scalar resolute of V in the direction of W is exactly equal to 1. So V minus this resolute, and there we go. So this 1, neg 2, 3 is the vector resolute of V in the direction of W, and 2, negative 2, negative 2 is the vector resolute of V perpendicular to W. So if I add these two together, the parallel plus the perpendicular, I should get back to V, which is what happened. Whew, it worked this time. Awesome. Okay, so now that that's happened, the way you would write out the answer to this question on an exam paper or an assessment is I'll just do it as a comment so it doesn't evaluate it. So I'll insert a comment. So the way you would write this is you'd say V equals, because you want to write it as the sum of two resolutes. I'll write it as 1, so I'll write it as a vector. So I minus 2j plus 3k. So that is the resolute parallel. Plus, I'll write the resolute perpendicular, which is 2i minus 2j minus 2k. So this is how you would answer this particular question. Okay, so now moving on to a possible exam question. So I've got respective to the direction of vector B. So I've got a vector B, and we're doing everything respective to that vector. The parallel and perpendicular resolutes of another vector A are as shown over here. I've got 2i plus 8j minus 4k and negative 6i plus 2j plus ck. Okay, so I've got two vectors over here, and what we're told is these two given vectors are the parallel and perpendicular resolutes. So what you have to do first is find the value of C, which is the unknown component, unknown k component of the second vector, and hence we have to state the vector A. Okay, so first things first is, if you recall, back in the first one here, I mentioned that the gray vector and the orange vector, which are the parallel and perpendicular resolutes respectively, they are always perpendicular to each other by definition. Okay, so if these two given vectors are perpendicular, it means that the dot product between them is equal to 0. So let's solve that equation. Menu 3, 1, let's solve, and dot product. So menu 7, C, 3, the dot product between these two vectors. So let's type the vectors as we are. Vector 2, 8, -4. -4, there we go. Along with the other vector. So I've got -6, 2, C, and here's the dot. So I've got the dot product here, but I want to solve it equal to 0 for the value of C. There we go. So C is equal to 1. So what that means is basically I've got these two vectors when they dot product with each other, and if I want to make sure that they are perpendicular, I need to equate the dot product to 0, and the value of C is of course going to equal 1. Now that I've got the value of C, we need to use this to find the vector A. Well, as I said before, the vector A is simply the sum of these two components. So what I might do is I'll quickly just go and copy these two vectors. So I'm going to use the Shift button and write together, which highlights that vector, enter to copy it and paste it, plus. I could have, of course, defined these vectors as well. Okay, so I can define the vectors as whatever letters I want, or anything apart from A or B, or even C for that matter. And then it can do this that way as well. So I'm going to add these two vectors together, but I'm going to now tell the calculator, please sub in C equals 1. The way I'm going to do that is use Control equal, press left for given, and then simply press up to highlight C equals 1, enter, enter again. There we go. So the vector A as required is neg4i plus 10j minus 3k. Okay, so moving on to the next part, which is linear dependence and independence. Now I know that this is a really tricky concept to not only learn, but also to explain and understand. Okay, so I'm just going to quickly summarize what's going on. Basically, if you've got a set of vectors and they're linearly dependent, I'm going to focus on the three-dimensional case with 3 vectors in it. If a set of 3 vectors is linearly dependent, it means you can take one of the vectors, let's choose C for this example, and express it as a linear combination of the other 2. So linear combination is basically a scalar multiple of each of the vectors A and B and add it together, or you can subtract it as well. Of course, that would require n to be a negative. So that is what linearly dependent is. That's the easiest way to understand. It's just that one of your vectors is a linear combination of the others. So if you try and solve that equation, C equals MA plus NB, and you end up with no solutions for M and N, then what that means is your set is linearly independent. And that is, you can't express any of the vectors as a linear combination of the others. Okay, so I've got some diagrams of here which help explain what linear dependence and independence is. If 3 vectors are linearly dependent, what that means is the 3 of them can span an entire plane or a line. So what that means is the 3 vectors, they all lie in the same plane, which means that you could take any 2 vectors or any of these 3 vectors, add them together and create any point you want on the plane. So I've got this plane over here, and let's say I've got a point 10, 8, 5. I could use a linear combination of these vectors and get to that point. When you've got a linearly independent set, what ends up happening is one or more of the vectors exists outside of the plane you're looking at. And what that means is you can't get to all the points on the plane because you've got one vector that's living off that plane. So that's one possible way to describe visually what's happening between dependence and independence. Okay, what I'd like to show you now is an alternative way that the CAS really helps with in terms of working out dependence and independence. Just a quick disclaimer, this is not on the study design at all. It's just a way to quickly check for dependence and independence. And I personally like to use it for multiple choice questions on exam 2. When you want a really quick way to determine dependence or independence, you can use a determinant. So if you take 3 vectors and put their components row by row into a 3 by 3 matrix and then find the determinant, And then if you get exactly equal to 0, this implies linear dependence. So if you get the determinant of this matrix and you get equal to 0, you will get linear dependence. If you get a determinant that's non-zero, so basically anything that's other than 0, it implies linear independence. Okay, so here we go. Let's look at an example here. So let's determine if the set I plus 2j plus 5k, I minus 2j plus k, and 2i plus j plus 7k is linearly dependent. Okay, so I'll just call these vectors p, q, and r. So p is defined as 1, 2, 5. Let's define q as the next vector, which is 1, neg 2, 1. And let's define r as vector 2, 1, 7. Okay, so I'll start off by trying to basically do C equals MA plus NB, except I'll use P, Q, and R in this case. So menu 3, 1, let's solve. R equals M times P plus N times Q, and let's solve that for M and N. And I actually get a unique solution. I get M equals 5 on 4 and N equals 3 on 4. So what that means is vector R is actually the same as 5 quarters times vector P plus 3 quarters times vector Q, and that is true. So this is a linearly dependent set. So they are certainly dependent. Let's quickly check the dependence using our determinants. So to get determinants, menu 7 and 3. Menu 7, 3 is determinant. I'll quickly add in the matrix. I'm going to press the template button and go to the 3 by 3 matrix there, and I'll basically choose 3 and 3. Let's put the vector components there. 1, 2, 5. I'm using the tab command to get quickly from cell to cell. 1, negative 2, 1, and finally 2, 1, 7. There we go. And my determinant is equal to 0, which means that I've got a linearly dependent set. There we go. 2 ways we can show that vectors are linearly dependent. Okay, so let's move on quickly to an exam question. So I've got 3 vectors here, AI plus AJ plus AK, 2I plus AJ plus AK, and 3I plus 4J plus AK. I want to find the values of A for which these vectors are linearly dependent, where A is not equal to 0. So for this one, I'm going to use the determinant method. So menu 7, 3. Let's put a 3 by 3 matrix as I did before. 3 by 3, and A, 2, A. The determinant looks really nice, actually. Look at that. That looks awesome. So I've got A, 2 A, 3, 4 A. I've got this upper triangle of vectors, of elements there, of A. Okay, so the determinant is this cubic over here. So I want them to be linearly dependent. So as I said before, to get dependence, menu 3, 1, I want to solve this determinant is equal to 0 for A, but I do want to make the restriction, control equal, that A cannot be equal to 0. So again, control equal, not equal 0, and there we go. So if A is equal to 2 or A is equal to 4, I will get a linearly dependent set of vectors. Now with A equals 2, it's actually really easy to see that is dependent because the top row, the first vector will be 2i plus 2j plus 2k. The second vector will also be 2i plus 2j plus 2k. In other words, I can get the first vector by basically multiplying the second vector by 1 and multiplying the third vector by 0. So yeah, as you can see, the first vector depends on the second vector that way. And with 4, you can use your other definition with your C equals MA plus NB. Okay, let's move on to the final bit of the session, which is vector proofs. Now, the CAS doesn't necessarily help with the actual steps of vector proofs. It can help when you've got vectors given to you, but when we have general vectors A, B, and that sort of thing without being specified, it's a bit trickier to use. What you can do, though, is use the geometry page and use dynamic geometry within that to verify some results. So some of the results that I find useful when using vectors for proofs are a couple of these ones. If you dot product a vector with itself, you get the square of its magnitude. If you dot product 2 vectors and you get 0, it implies that the 2 vectors are perpendicular. That's, of course, assuming that neither vector is the 0 vector. If one vector is a scalar multiple of another vector, it implies that the two vectors are parallel. And finally, if two vectors are equal, this implies that the two vectors are, of course, parallel to each other, but it also implies that their magnitudes are the same. Okay, so let's look at a quick couple of examples. First of all, we've got to verify that the angle subtended at the circumference of a circle by its diameter is a right angle. So this is the classic proof. There's multiple ways to do this proof, but I'm going to show you how to verify this using dynamic geometry. So what I've got here is a geometry page. In a geometry page, I can draw a circle by going Menu, 5 for shapes, and then 1 for circle. What I do is I'm going to pick a point, which is the center, and then simply go out to get a circle like that. So now I want to get a diameter. To get a diameter of a circle, I'm simply going to go Menu, Points and Lines, and I could get a segment, but a segment will give me a radius rather than a diameter. So what I can do is I'll choose Line. So the way to do a line is I can choose the center of the circle and then simply pick any point on the circumference. I'm going to pick one about there and then press Escape. Okay, so I've got now a line that's passing through the center and one end of the circumference, and just grab this other end and pull it over here. Before I proceed any further, as you can see, this is much easier to do on the computer software, either the student or teacher version. You can do this on the handheld, but it'll just be a bit trickier. So if you are doing this, try and do it on the computer version. Okay, so I've now got a diameter here, and as you can see, I can move this and it will always remain a diameter. So let's create a triangle that's subtended at the circumference by this diameter. So to create a triangle, Menu, Shapes, and Triangle, and I'll just click this intersection point, which is the start of the diameter, go to the other intersection point, to the other end of the diameter, and then pick a point on the circumference. As you can see, it says Point On, and then press Escape. So what I've done is I've created a triangle that's subtended by the diameter, subtended at the circumference by the diameter. Now I see this extended over here. I can actually go to the line there, right-click, or Control Menu on the handheld, and simply hide it as shown over there. So after I've hidden that, I've now got my triangle over there. Okay, so to verify that it's a right angle, I'm going to use the measurement tool. Menu, Measurement, and go Angle. So here we go. Here's, to get angle, what you have to do is you have to pick the first end of one of the angle lines, and then the second point is where you want the angle, and the third point is where you want the other end. So I'm going to click this point, then go to that part of the triangle, and then go to the other end as well. Then press Escape. And as you can see, as I move the triangle around, I can move the location of that vertex. No matter what I do, I can even increase and decrease the size of the circle. That angle always remains 90 degrees. So you can use your vector methods to prove this using the proper steps, but to see it dynamically and verify that it is true, you can use dynamic geometry. There's a couple more examples that I've got as well, but we've unfortunately run out of time. So I will leave it over there. So thank you, as always, for tuning in. Hopefully you've learned something really useful over here, and you can download the worksheet for this session later on after the webinar. You will get the link. And yeah, thanks for joining in, and good luck with your studies.